So our goal for this lesson is to define oxidation and reduction, write simple half reactions, and write a redox reaction using half reactions. This is just the tip of the iceberg for our electrochemistry unit, so this will get us started. Electrochemistry is the branch of chemistry that studies electron transfer in reactions. Electrochemical reactions are the most common types of reactions in both living and non-living systems. So for example, photosynthesis, cellular respiration, and metabolism as living examples, and corrosion, combustion, and formation of metals as non-living examples. Make sure you take down all of the stuff that's underlined and bolded and blue. Those will fill in the blanks in your notes. Oxidation and reduction half reactions. A half reaction is a balanced reaction that represents either the loss or the gain of an electron by a substance. Half meaning there's two halves to one reaction. We will always have two. It's balanced by coefficients, where the same number of atoms or ions are on each side of each element is on both sides of the reaction, and it's balanced by electrons, so the same total charge occurs on both sides. Like I said, half reactions imply that they're one half of the whole. So oxidation and reduction summarize the electron transfer taking place during a redox reaction. Adding the half reactions together gives you the net ionic equation for the redox reaction. So looking at that definition for oxidation and reduction. Oxidation is the loss of an electron. So we can tell that it's an oxidation half reaction because the electron is in the product, So for example here, magnesium as a solid can become magnesium as an ion, the 2+ ion charge, but it has to give up 2 electrons to do so. We can write that as a half reaction. Fun fact, oxidation is named for a metal reacting with molecular oxygen, like corrosion. Reduction is the opposite. It is the gain of an electron. So an electron must be a reactant. So we see here iron 2+ can gain 2 electrons and become iron solid. So the redox reaction is the oxidation and reduction half reactions added together, and electrons must be canceled out. You will never see electrons in a redox reaction. They're the behind the scenes. So what we're going to do is we're going to add these two reactions. So we get Mg solid and Fe2+ aqueous and 2 electrons as reactants, making Mg2+ aqueous, 2 electrons, and iron solid. Now, cancel what occurs on both sides. So it has to have the exact same state, the same charge, etc. So the only thing that can cancel here is electrons, which is great news because I just said it can't occur. They can't be there in a redox reaction. So writing it out, Mg solid and Fe2+, my best printing for you guys, makes Mg2+ and Fe solid. So this is what we would see as a net ionic equation, but the half reactions that we're seeing up here are what's going on behind the scenes. So to remember what oxidation and reduction mean, we have the I guess mnemonic, I think is what this is called. Leo the lion says grr. So Leo is loss of electrons is oxidation. And grr, gain of electrons, is reduction. So G-E-R-L-E-O. So I write this, Leo says grr, at the top of basically every page when I'm working on an electrochemistry problem still. So I expect to see this on most of your work as well. Just as a reminder, it would be a shame to get the easiest definition wrong. Okay, so some practice. Balance the following half reactions for atoms first, then electrons to balance the charge. Select the correct redox definition for the half reaction. So what we're going to do here is our first one. We have zinc solid going to zinc 2+. So the zinc ions are balanced, the zinc atoms are balanced. Now we just need to balance for charge. So over on this side, there's the total charge of nothing, 0, and 2+ on this side. So what we need to do is we need to add 2 electrons to the product side. Now, Leo says grr, loss of electrons is oxidation. Now going through in this fashion, we're going to keep going. Chlorine is Cl2 and it makes Cl minus. So we need to balance for chlorines before we start balancing for electrons. So now the overall charge on this side is still 0, and over here we have 2 negative ions. So that's a 2 minus charge overall. With that, we need to add 2 electrons to the reactant side. Gaining electrons is reduction. So continuing on, X's are balanced here. It doesn't matter what kind of atom that is. So that's a 5 negative charge on this side, a 7 negative total charge on this side. So we need to add 2 electrons here. Again, reduction. Coppers are balanced. There's 1 copper on both sides, a positive 1 charge and a positive 2 charge. We need to add 1 electron to the products, making that oxidation. And to balance over here, we're going to add 8 S2s. With that, we have a negative 16 charge over here because 2 times 8. So what we need is we need to add 16 electrons over here, and that'll be oxidation. All right, so what we're going to do here is we're going to write the balanced reaction or the redox reaction using half reactions. So write the balanced half reactions and balanced net ionic equation for the reaction of silver 2 nitrate with a solid strip of zinc. So what we're going to do, just one second, it should just be silver nitrate, is we're going to write Ag, NO3, I don't actually need brackets, AQ, and zinc solid, reacts to make zinc nitrate, and this time we do need brackets. Don't forget to drop and cross charges, and silver. So this is a single replacement reaction. We're going to need 2 and 2. Write the half reaction for each substance that undergoes a change in its charge. So we can see that nitrate didn't actually do anything. Nitrate is NO3 on one side and NO3 minus on the other side. So there's no change in charge. What we are going to write out though is that silver went from silver 1 plus, thinking ions here, to silver solid. All right. Then what we also have is that zinc started as a solid and became zinc 2 plus. Balance the number of electrons in both reactions. So we need to, determine the number of electrons lost or gained, and we're going to add those in. So we need to add an electron on this side to balance and 2 electrons on this side to balance charges. Now to apply the labels, I need to write Leo says grr. Gaining electrons, this is our reduction half reaction. This one's losing electrons, so it's our oxidation half reaction. What we're going to do next is it says we need to balance the number of electrons in both half reactions by multiplying 1 or both half reactions by a coefficient. So what we want to do is get the coefficients in front of the electrons to be the same. So what that means we need to do is multiply our silver reaction by 2. Okay, so that we get 2 electrons. So we're going to get 2 electrons and 2 silver ions make silver solid. And then I also have zinc solid making zinc 2 plus and 2 electrons. So I didn't have to do anything to that one. Last step is like we did before, we're just going to add those half reactions together. I'm going to cancel my electrons first just because I don't want to write this out 1,000 times. So just like Hess's law here, we're going to cancel before. So if it's a reactant in one reaction and a product in another, we can cancel them before we even start writing. So we get 2 Ag plus and zinc solid makes zinc 2 plus and Ag solid. So notice that if we had crossed out our spectator ions in our regular balanced equation, we'd actually be left with the exact same equation on the bottom. So our redox reaction is strikingly similar to our net ionic equation. We just looked at the behind the scenes with where the electrons were being transferred. So what's happening is zinc is giving up 2 electrons to become zinc 2+. Those 2 electrons are used by silver 1+ to become silver solid. And it's enough electrons to get 2, oops, I forgot my 2 up here, silver solids. And I did it down there too. All right, so these are practice ones. What we're going to do is we are looking to write the reduction half reaction and the oxidation half reaction and the net ionic, which is also known as our redox reaction. So what we're going to get here is I2, which is a solid, and 2 NaBr, AQ. So I'm going to need a 2 there. Leo says Gur. What we have here is sodium is actually our spectator this time. Sodium's charges didn't change. And bromine, I do believe, is gaining electrons. Now, I only know that because I can do this in my head a little bit quicker. But what I'm going to do is I'm going to write it up here. If you got it in the wrong spot initially, don't worry about it. Just switch your things around. So Br2 is going to make 2 Br minus. Remember, we balance for atoms. And we need to add 2 electrons to this side of balanced charges. Then on this side, we're going to have I2. Oh, sorry. I minus, 2I minus, making I2 solid and 2 electrons. The net ionic is Br2. And 2 iodine makes 2 Br minus and iodine solid. Electrons canceled. All right, over here, nickel is going to be losing electrons, and I solid is going to make Ni2+. It's its most common charge, and 2 electrons. And iron is going to be reduced, Fe3+, and 3 electrons will make Fe solid. Now, you guys will have done this step by step. This is your final answer. We do need to multiply both of them here. This one's got to be multiplied by 3, and this one needs to be multiplied by 2 to make sure that we get 6 electrons. It's the lowest number we could have done. So we get 2 Fe3+. I'm going to drop my states here. I'm running out of room. And 3 Ni solid. I do expect to see your states though. Makes 2 Fe solids and, oh, what's that? And 3 Ni2+. All right, so your homework today is the 12.1a section of your homework. I do believe it's only 1 page. It's in your homework booklet.